Hello, my name is Diego Blas. I am a senior lecturer in KCL, King's College London, and I'm going to be your leader of the module on Introduction to Dark Matter. It's going to be composed of 5 lectures of 50 minutes each, more or less, and we're going to explore different aspects of this fantastic problem of modern science, in particular of modern particle physics. So, about the structure of the course, the way I'm going to teach it is not with the slides, but with a more traditional theoretical tool, which is the Blackboard. And in this case, it's going to be a virtual Blackboard. You also have my notes that you can consult. My lectures are 100% based on my notes. In the notes, there are also other references that you can look at, and other lecture notes that are quite interesting. Of course, in this short course on dark matter, there are many aspects that I'm not going to cover. If your favorite topic is not covered, I hope that in the notes you can find some reference, or otherwise you can email me and try to find the place to learn it. Very good. So yeah, that's me, Diego Blas, and I am at King's College. This is the email address where you can find me. Okay, my name at kcl.ac.uk, and as I said, there are my PDF notes and also my problems that will be distributed among the crowd. Very good. So I'm not a particle physicist. I am more a gravity person with some interest in dark matter, more in the astroparticle part of it, in the galaxies or in the cosmological setups. But this module is going to cover both astroparticle and astrophysics probes of dark matter, astrophysical, and also a little bit of particle physics, but more on the production mechanisms for Cosmo, right? Not on the searches for in LHC or other labs. Okay. Very good. So my model is divided into 5 chapters. First one is going to be, it's 6 because today I'm going to first start with a 0 part, which is a bit of 0 order motivation for why to explore dark matter. And then we're going to move to evidence for dark matter here. Then we're going to study some properties as a sub-part of the first section. Then, secondly, we will explore thermal production. One of the most important things about dark matter is that there is a way to produce it naturally in the early universe without having to invoke new mechanisms. So the same mechanisms that produce ordinary matter can also produce dark matter, and that's why the dark matter problem was or has been very, very intensely studied by people also doing particle physics, because the physics that you need for one and the other are very close to each other. This is not always the case. There is a class of dark matter models called axions, which are very popular nowadays, or axion-like particles, ALPS, that are quite different from the particles in the standard model, in particular if you want them to be the dark matter. And we will explore them a little bit, not too much, but since it is a hot topic that you may have heard of, I wanted to give you some, at least some taste of what they are and why they are important and why they are different in many aspects from other dark matter candidates. Yeah, that would be like a, something just to give a pause between the thermal production in WIMP models to the direct detection. Some, of course, some little information on how to directly detect WIMPs in the lab, okay, and which is also, by the way, a very important part of the WIMP. WIMP are weakly interacting massive particles, favorite candidate for dark matter, and you will see that both because they are easily produced in the early universe, easily in the sense that with the standard tools, and because they may be detected on Earth easily also. This made them preferable candidate of dark matter. But nature can be what it wants, right? So who knows if this is a real miracle, or it's just a coincidence that these candidates exist. Actions have their own miracle. I don't know if we will be able to explore it in some detail. And finally, I left some time at the end of the lectures to other aspects of dark matter, ideas on detection, and very briefly maybe something on the indirect detection, but it is not going to be covered in this module. It's basically impossible to have a kind of coherent module with all these things in 5 hours, unless I rush a lot, and that's not the point, right? Yeah, there will be also problems that I distributed. They are based on the lectures. Some of them are based on problems from the previous lecturer on this, David Cerdeño. You solve them in the problem sessions, and there will be solutions for them. They may be a bit different from the kind of problem that you're used to. So you have the internet to look for stuff, you have yourself, the group, so please be patient, and I hope they are interesting enough for you to look at them and solve them. All right. So, chapter 0. Why you want to study dark matter? When I say you see, I mean an experimental particle physicist. Well, of course, first is because it's a very interesting topic. It is part of the cosmological model. So there is in the same way that there is a particle physics standard model, there is a cosmological standard model called lambda CDM. And you see that here there is already CDM. So there is lambda, meaning that you need for this model something called a cosmological constant that is not going to be covered by me. And also there is CDM as the second main component of the universe. So you see that it's very important for whenever you want to understand the evolution and origin of the universe, to understand dark matter. Okay. Without dark matter, you cannot reconcile theory with observations in the problem of trying to put together the data from cosmology and astroparticle physics, astrophysics in general. There are, of course, some alternatives to dark matter, but let's say that they are not so much favored as those containing dark matter. Yes, I don't want to say more about this. Second reason why you want to know about dark matter is because the standard model is not complete. There are physics beyond the standard model, and dark matter may be one of the physics that is both theoretically predicted and experimentally needed. There are some corners for BSM, one of them, let's say, neutrino masses. Another one called the baryon asymmetry of the universe, BAU. Okay. There's also quantum gravity. And finally, there is dark matter. All these are new elements that you need to put on top of the standard model of particle physics to understand our world. But they can also, in the sense that to understand them in the sense of experimental data, but also they can be connected to other aspects of BSM, like the hierarchy problem. Right. And this is, by the way, this connection is the connection that, for instance, supersymmetry or other nice theories beyond the standard model may produce. So those are theories that may be able to solve a theoretical issue of the standard model and also a experimental experimental puzzle of the universe. Quantum gravity, then, sorry, should not be here. It should be here. Okay. Yeah. back there. Yeah, technology. All right, so I think that's basically all. We don't have that much time, but there is, of course, a lot of motivation for you to, to understand this problem. And not only you, but CERN itself is looking for dark matter intensively in many experiments. Okay, there are many dedicated groups in all the big experiments, and they make a great job. So in the notes now I give you a series of videos, lectures that are very interesting, and they cover several aspects of dark matter. And now we're going to start with the program, okay, after 10 minutes, which is okay. So it's going to start with evidence of dark matter. Yeah, by the way, I will share my slides with you, of course, at some point. So, since I have a gravity background, I always enjoy to make the analogy with what happened with the dark matter we already had in the solar system. Yeah. So in the solar system, we had an observation which had to do with the orbit of Uranus. Okay, so Uranus had an anomalous orbit. As measured in the 1840s. What do I mean by that? That you had all the matter content of the solar system taken into account and computed the orbits of Uranus, then you see that the orbit was not corresponding to the Newton's law of gravity, taking into account all the mass, right? So there was a mystery there. Yeah. So Uranus, as I said, sorry for the break. It has this anomalous orbit, and what could be the cause? So there was a hypothesis by an astronomer called Leverrier, saying that the reason why the orbit of the Sun, that's Uranus, the reason why the orbit didn't correspond to the ones of Newtonian physics was that there was another planet, okay, with an orbit very well defined that was modifying the gravitational potential on Uranus. This was predicted in 31st of August of 1846, and amazingly enough, on 23rd of September of the same year, since the orbit was so well predicted, they put telescopes in this direction and they found it. So Leverrier found which planet? Okay, it found sorry, Neptune, because I was gonna say Pluto. No, Neptune. Okay, so Leverrier found Neptune this way. In which sense this is analogous to dark matter? We're gonna see that dark matter corresponds to some missing mass that is needed to account for the observations on gravitational phenomena. Unfortunately, there was also an anomaly in Mercury. So this is the Sun, by the way. Mercury has also an anomaly in the orbit. The same scientists predicted an inner planet called Vulcan, but if you remember the planets from school, there is no Vulcan in your memory, and this is because this planet doesn't exist. The reason why there is an anomalous orbit for Mercury is that the Newton's law is no longer valid at a small distance from the Sun. Okay, so this is something very important. Well, very important. It's something that is interesting about dark matter, is that in this case there was a possibility, was saying, okay, let's modify. So this is the gravitational potential from the Sun, so let's modify it by adding an extra planet. All right, whenever I have an anomaly. That was the strategy from Le Verrier. So certainly, if one used this potential to fix one of the orbits, it cannot fix the other one. Okay, why? Because this is 1 over r potential, okay, and it's not going to be influencing very much whatever happens in the inner orbits. So that means that by adding one single new element, Neptune, you could not fix the other element, Vulcan. So you need a very complex, at least, well, there are 2 phenomena and you need 2 new planets to explain them. This is not very nice. The dark matter paradigm, and one of the reasons why it is so compelling, is that there is one hypothesis that there is some mass missing, or there is some gravitational phenomena that we cannot understand in different aspects, in different sets of the universe, and they are all fixed by a single hypothesis. So dark matter fixes several problems. What problems? Problems at different scales. So that's, as I said, this is a key reason why it is not trivial to fix the dark matter problem with just modifying the law of gravitation. The law of gravitation that fixes Mercury because it's very close to the Sun, the same. So it fixes Mercury by modifying general relativity, Newtonian potential. And this is something that it is of the order of the gravitational potential square. All right? So it is only important close to the Sun and not far away from the Sun. The models that typically modify gravity, which are the models that have been also used to claim that you don't need dark matter, typically they solve one of these problems because they have one only scale. In this case, in the case of general relativity, the scale is the strength of the gravitational potential. So if the gravitational potential is stronger, in general relativity, the corrections are bigger. But the correction of general relativity for Mercury cannot work for Neptune, and the other way around. All right. I hope that's giving you an impression that the dark matter problem is, well, and we're going to see now that it is a multi-scale problem, and it is not easy to solve with a single hypothesis, and that's why the WIMP or other dark matter candidates are such compelling explanations. And we are jumping now to the first of the dark matter evidences. Okay, so we have evidence of dark matter. There was this little explanation of motivation of other places where dark matter was used in the universe, and now dark matter evidence. So the first evidence is going to be dark matter in galactic curves. So as I said, I'm going to draw things. You can check them on the notes to see more precise drawings. And where does this come from? Well, this evidence comes from the fact that if you have a source of mass as a function of r, and you want to compute the velocity of an object in a circular orbit, it turns out the velocity square is equal to gm, the mass at this radius, total mass up to this radius, and then divided by r. Okay, this is a result of classical dynamics, where of course v is the velocity, g is Newton's constant, and as I said, r is the distance from the center. Yeah, and this is, by the way, yeah, this is only valid if the distribution is spherical. Okay, so in general, this is going to be more complicated. So if it is spherical, then this law is satisfied. Okay, so why I draw a generic in principle distribution is because we are gonna use this theorem also for galaxies which are not exactly spherical, but you can correct it, okay, appropriately, and these corrections are not gonna give you any new information for what I want to use it. Okay, I only want to use it to motivate dark matter. So in principle, this is enough. So only for spherically symmetric concentrations, this law is satisfied, but that's enough for us. So the simplest example where this is valid are the orbits of planets in the solar system, where you can check that if you plot velocities versus radius, indeed they follow exactly v as 1 over r to the 1/2, because in this case there is just mass in the center, the sun, and all the rest, yeah, so the m is fixed and the rest goes like this. What happens if we have a distribution of mass where mass, which is given by what? By mass density, okay, energy density if you want, multiplied by r cubed, right? So what happens if rho is constant? So imagine that you have a kind of bulge, then in this case the m is going to grow as r to the cube and v is going to grow as r, okay? So if you have a concentration of mass which is a constant, v grows like r. You can say that a galaxy may have this internal structure, right, where things are quite concentrated. It's not, as I said, completely true, but this is something that you can imagine. And this means that when you go to the kind of plot that you expect in galaxies of radius versus velocity for different traces, let's say stars, or different traces of the gravitational potential, you would expect something like it grows like r at the small radii, because that's where if you want, let me draw it with this color. So here, oops, doesn't work. Oops, it doesn't want to work. So here, let's say here is where the galaxy, most of the mass is concentrated. At some point you reach the outskirts, and from the outskirts you expect the 1 over r to the 1/2 to dominate. Is this what you see in data? Not at all. In data, what you see is something like, yeah, this is true, but then there is typically a plateau, and then only later on, yeah, there may be some drop. So that means that there is something outside of the galaxy that also contributes to the gravitational potential that dominates the dynamics of these outskirts of the galaxy. What can it be? Well, we know already something about it, okay, because we know that this is v constant, okay, and to have v constant, rho has to go as what? Well, let's go. You can plot, you can use this equation here, okay, and if v is constant, m should go as r, a should go as r, rho should go as 1 over r squared. Yeah, so let me write it properly. This is the way it should, as I said, the new structure should behave if it's going to explain this data of rotation curves in galaxies. Yeah, you may notice that I stop from time to time. That's because since we are recording all this in blocks, it is it is better that I stop sometimes to think about what I want to say. I hope that's okay. All right. So yeah, rho to the 1 over r squared is what you need, and also in this case it turns out that you need it to be spherically symmetric. This to be spherically symmetric. By the way, you can look at this with real data in the figure 1 in the notes. Spherically symmetric at large distances, and in the middle there is the galaxy. The galaxy is typically, for example, our galaxy is 10 kiloparsec invisible matter, the matter that is generated this disk, and the rest of the halo is distributed not in a disk as matter in our galaxy, for instance, but in a spherically symmetric distribution. And we will see this already tells us something about what dark matter can and cannot be. The fact that you need it to be distributed in a spherical halo, it's called a halo, dark matter halo, and the size, for instance, of the halo in our galaxy is believed to be of 100 kiloparsecs as opposed to 10, right? So much higher, much larger. So this dark matter halo has to be spherically symmetric. What does it mean? It means that when you, in galactic dynamics, when you generate something which is spherically symmetric and is rotating, it may turn into a disk if you allow it to dissipate energy through photons. That's the way we believe, well, everyone believes, that spiral galaxies are formed. In the case of dark matter, this cannot be the case. You cannot have spiral structures of dark matter. It has to be spherically symmetric. This already tells you that dark matter cannot efficiently interact with photons. It cannot efficiently emit photons, because if it did, that would generate disks of dark matter instead of halos. So you see that the observation from galactic dynamics not only informs us about the existence of dark matter, but also about some of its properties. We will see more of this in the following. Another place where we get information about dark matter is in the dynamics of galaxy clusters. So in the universe, there are big structures which are bounded by gravitational interaction, and they're called galaxy clusters. They contain several galaxies which are kind of orbiting around each other. The typical distance between these galaxies is 1 megaparsec. By the way, I introduced parsec and megaparsec and kiloparsec. Yeah, I guess that is you're already used to the notion of parsec. If not, please look it up, and if you have any question, please let me know. So those are the typical distance, and the box of the size of this cluster of galaxy is typically 10 megaparsec. Okay, so quite big as compared to, remember, what we said before our galaxy is. Okay, and those are, as I said, in a kind of orbital motion around each other. Of course, there are so many of them that it's not that there are one orbiting around each other, but there is this kind of motion that keeps things together in a big structure. In this case, one can use what is called the Viralized theorem, and you will look at it in more detail in your problems. Okay, and the Viralized theorem tells us that the average kinetic energy of a stationary situation is equal to minus 1/2 the average potential energy. This is a very beautiful result of classical physics, and it only requires some equilibrium, if you want, some stationary situation that, in the case of the globular clusters, the galaxy clusters, is achieved in some of them. Okay? You expect that they have already had enough time to accommodate to this, to the hypothesis that you need to prove the Viralized theorem. Basically, that they are already kind of stationary. What is the kinetic energy? Well, in this case, simply kinetic energy 1/2 of the sum of all the masses, velocities, masses squared over 2, potential energy, all the pair of masses interacting with each other, and this is nothing but Newtonian gravity, Newton's law of gravity. This is, well, of course, this is a fraction, right? Okay, and you see that this is something you can compute. The only thing that is missing is what I mean by this average, and the average is an average on time in principle. So from one initial time to final time. Okay, so you take a quantity, you average it on time. Of course, you cannot do time averaging in cosmology. What you use is what is called the ergodic hypothesis, to claim that any average in time corresponds to an average also in space. So you basically average the different configurations that you have around and try to look if they correspond to this average law of Viralized theorem. Furthermore, it is very difficult in astrophysics to do statements with one single system, because there are so many systematics you don't control that it's really tough to get convinced that something is a new phenomena or just a new systematic. So the idea is that what we're going to show here has been observed in many systems. And in many systems, what it has been observed is that this law doesn't hold. So there is more potential energy, okay, than what corresponds to the kinetic energy of the stuff that you see. So there is more, if you want, dark stars or dark galaxies, you can think about it, it's going to be dark matter, okay, that are modifying the orbits, but in a way that, yeah, you cannot put together in this law, because you don't know which are the masses, you don't know which are the kinetic energy of these new objects, right? So in principle, if you knew everything, this should be satisfying, okay? But there is not something else. This was put forward by a scientist called Zwicky, and that was maybe the first time that modern dark matter was needed in astrophysical observations. And I don't want to go forward without saying that one of the main scientists observing galactic curves and putting them on a serious, a serious footing was Vera Rubin, a fantastic observer that you should know, and if not, please look her up. There is something more also about about the galaxy clusters, and it is that you can indeed observe the mass that generates the gravitational potential by other means. So not only, so what we are doing now is that we see the galaxies, we count them, and from them we know, in principle, you try to know the masses, the velocities, okay, and the Viralized theorem is going to relate all these numbers. However, if there is something else called gravitational lensing, allowing to measure the mass of these huge structures by the following phenomena. So if there is a source of light behind and it shines light, this light in general relativity deviates its trajectory when there is some source of gravity. Okay, and this deviation depends really on how much, mass, well, this is a cartoonish way of saying it, but it depends on how much mass there is inside, because it's the gravitational field that makes this light bend. So you can now observe this bending of light, this is called gravitational lensing, then you will be able to understand how much mass there is inside. So you put one more observable here, like total mass. And already from this information, you see that there is more total mass than the amount of mass that you measure just by luminous mass. And remarkably, the conclusion is the same as Zwicky had, right? That you need more mass, and this mass is of the same order of magnitude that the one that you need to accommodate with the Viralized theorem. So this is a great observation. That indeed, as I said, the different pieces of dark matter come together very nicely. Very good. So let's continue with the next evidence for dark matter, and it's going to be in the collisions of galaxy clusters. So you already know that galaxy clusters exist, you know that they are big, but now you can also look at them in interaction with each other. Not live, but you can see that there are some clusters, and I invite you in the notes, I give you the video you can watch, which is very nice, about the situation where you have a cluster, you have a different cluster, and they go and hit each other, and in these dynamics, you know, something very complicated may happen. What may happen in these dynamics? Well, it depends on the species that you are looking at. So in this in this cluster there is gas, there are galaxies, and there is dark matter. Okay, I'm going to put dark matter in blue. As this goes and collide, gas interacts as every particle in the standard model interacts, so it's going to be producing a shock wave when it gets in contact with each other, and it's going to kind of stick in the middle and be very hot, while dark matter, since it is a substance that in principle is not interacting efficiently, another way to discover the dark matter properties is going to go through, okay, which means that the result of this collision is a new configuration where dark matter is far away from each other and the gas is in the center. This is gas, this is dark matter. It looks like a smile. Okay. So, are there such structures in the universe? Yes, there are such structures. And how do we detect them? Well, the gas is detected through X-rays. So this gas is going to be gas that has gone through a violent collision, so it's quite energetic. So this can be detected through X-rays surveys. And the dark matter is detected in the same way that we detected it before, through gravitational lensing. So there is dark matter will generate a gravitational potential, and if you look at a source of light behind, I'm going to use a different color. Light is going to be deviated, and you're going to be, if you are able to follow these trajectories, you are able to know how much mass there is in total. And the total mass requires the blue component. So you cannot explain the trajectories of light without the blue component, and not only that, it has to be where it is. So this is the way you understand that what you see in the sky corresponds to a collision of a cluster of galaxies in the past. I leave you as an exercise to think about what happens to galaxies themselves. Right, because also here in the clusters of galaxies, there are galaxies. So there is gas, like it's all over the place. There are galaxies distributed, but few of them. Remember, 10 megaparsec distance, typical distance is 1 megaparsec. If you want, you can compute the cross section and understand that galaxies are going to go through without seeing each other. So the galaxies are also far away, basically, as dark matter is. And finally, there are the cosmological probes of dark matter. This may be a bit farther away from your background, but cosmological probes, but that's very important. Why? Because here we are talking about megaparsec scale. Here we are talking about kiloparsec scales. So as I said, it's a multi-scale problem, the problem of dark matter. And you can go to gigaparsec scale, which is the cosmological scale in the universe. And in this case, yeah, I also give you as an exercise to have a look at how dark matter can influence the observations. There are several of these cosmological probes. All right, let me just give you the most impressive one. The most impressive one is the cosmic microwave background. Or CMB, and its connection to modern structures in the universe. So the cosmic microwave background corresponds to photons that were emitted when the universe was cool enough such that electrons and protons combine into neutral atoms, and then the universe becomes transparent to radiation. So this is called recombination. It happened almost 13 billion years ago, or more than 13 billion years ago. And before recombination, the universe was a soup of electrons, positrons, and photons, basically, also neutrinos and everything, but this is the most important piece for us. After recombination, then the photons propagate freely and arrive to us. And this has been detected, so that's one of the most amazing detections of history, I would say. And you see spots of this radiation in the sky, some of them hotter, some of them cooler. And the average difference between these two, hot and cold spots, has a energy density. So remember, those are radiation, so you can translate energy density into temperature of the order of 10 to the minus 5. So there is the cosmic microwave background has a temperature of 2.7 Kelvin, and on top of it there are small fluctuations. Yeah, I didn't tell you what this is. This is basically, this is the angular, what you see in the telescope. So you could do different mapping, but you point at a telescope and look for this, you will see a small a granular structure of this typical intensity. Okay, so this is telling us that the universe a bit more than 13 billion years ago, giga-years, was incredibly homogeneous and isotropic. Okay, because basically all over the place in this observations you are seeing the same temperature, and all the small fluctuations are of the order of 10 to the minus 5 with respect to the 2.7 Kelvin. This is very different from what we see today. So basically, this picture here of very small fluctuations evolves into what? Into the galaxies, clusters of galaxies, and so on and so forth. For this to happen, you need a force to start clumping together matter. This is gravity, right? If you just consider, what you observe in the CMB, and you evolve it in time, you don't generate enough of the structure that we see today in the universe. So you need something else. You need some new component to make gravity more intense and generate the galaxies, or what is called the large-scale structure that we see today in the universe. Of course, this points out that we need more mass in the cosmos, and dark matter is here to help us. Not only that, this dark matter is exactly at the level that is also required for the other observables. So observations at the gigaparsec scale, which are the biggest scale in the universe, also require dark matter to be explained. All right, and typically this is in cosmology represented by a number called omega dark matter h squared, and you will see that if you take the latest data it is very well determined. What is omega? Omega dark matter is given by the density, energy density of the dark matter divided by average energy density, which is called average critical energy density, and this is basically 10 to the minus 6 GeV per centimeter cube. So you want to know how much dark matter there is in the universe. The only thing you need to know now is H. H is a factor that cosmologists use to avoid having results in a, in a, how to say, less, more cosmology independent way. So to have them in a more cosmology independent way, they typically use this H, and this H is for our universe 0.7. So if you put all this together, you see that how many particles of dark matter in terms of GeV there is per centimeter cube, so very little. So there is less, very, very little dark matter in the universe, and that's going to be a problem for data detection. But this is, you put all together, because dark matter is distributed in such big structures, it's also going to mean that dark matter may be dominant in the large scales. All right, and yes, so we are gonna now, before closing this first lesson, start exploring what are the dark matter properties from observations. The first one is that dark matter should be dark. Okay, meaning that it cannot be interacting. You want interactions with standard model should be quite small. Otherwise, we would have seen them already, no, in the lab, and this is not the case. And not only that, with a strong interaction of dark matter, you would have seen it in the cosmos, and there are many bounds for this. Okay, there are many bounds. Typical interactions should be always smaller than electroweak scale. Yeah, because if you have a new candidate at the electroweak scale, you have seen it. But there are other possible interactions, like the charge of the dark matter, for instance, is bounded, and there are some numbers, like, for instance, you are curious, mass should be quite small. Yeah, you can also imagine that if the dark matter is charged or it has interaction with the standard model, it will modify collider observations, it will modify stars, it will modify basically everything in the universe. So basically, dark matter should be dark, in the sense that it is very, very weakly interacting. Depends on the candidate. This may be more or less constraining. For WIMPs, I will show you some plots on how constrained this is, and for other particles, this can be a bit less stringent. And since these videos are supposed to have 50 minutes duration, so let me finish here, and I will continue with the next property of dark matter, which is that dark matter should be cold. Okay, so dark and cold. So see you in the next video. Thank you.